to launch 2 human beings into orbit. In the commander's seat is John Young. He is a veteran astronaut, chosen to lead this highly unusual test flight, based on his extensive experience in the Gemini and Apollo programs. Beside him sits pilot Robert Crippen. While deeply trained in the simulator, Crippen is a rookie taking his very first trip to space. Their objective is to endure a 54.5-hour orbital test flight. The catch is that they are flying a vehicle that has never once left the Earth's atmosphere. Before this moment, every American crewed spacecraft program conducted uncrewed orbital test flights first. By skipping that step, NASA placed Young and Crippen in the position of ultimate test pilots, riding a totally unproven system. The system waiting for them on Launch Pad 39A is massive. The Space Shuttle stack towers above the pad structure, completely different from the single-column rockets of the past. This diagram shows the integrated launch configuration, the reusable orbiter, 2 solid rocket boosters, and a single external tank. The gross liftoff weight table lists a total mass of nearly 4.5 million pounds. To lift this, all 5 engines must ignite simultaneously at sea level. Without data from an uncrewed flight, engineers had to rely entirely on static ground simulations and computer models to predict how these 3 connected elements would handle the extreme forces of liftoff. The sheer complexity of this digital and mechanical integration caused an immediate delay. On April 10th, a microscopic timing error in the general-purpose computers forced ground control to scrub the initial launch attempt. A tiny software mismatch halted millions of pounds of hardware. It proved how heavily reliant the entire architecture was on every single system functioning in perfect predicted sequence. 2 days later, Columbia finally clears the tower. The solid rocket boosters generate a combined 6.6 million pounds of thrust, sending intense, violent vibrations through the entire structure as the vehicle accelerates upward. In under 6 seconds, the shuttle clears the launch tower. At that exact moment, control of the flight shifts from the Launch Control Center in Florida to Mission Control in Houston. This chart tracks the dynamic pressure on the vehicle as it climbs. You can see the sharp peak labeled Max Q. To prevent the aerodynamic stress from tearing the ship apart at this peak, the main engines temporarily throttle down to 65% thrust. As they push through the atmosphere, the flight data reveals an immediate deviation from the ground models. The 2 solid rocket boosters are actually generating more thrust than the simulations predicted. Looking at the post-flight analysis report, this extra thrust forced Columbia into a lofted trajectory. As a result, the boosters burned out and separated at an altitude 10,000 feet higher than planned. The main engines continued to fire until they depleted the external tank. Once the empty tank was jettisoned, Columbia completed 2 brief burns with its smaller orbital maneuvering engines, successfully circularizing its path around the Earth. The ascent proved that real-world physics will always deviate from ground simulations.
The vehicle was forced into an untested flight profile on its first day, yet the airframe was resilient enough to absorb the extra energy and keep the crew safe. Safely in orbit, Young and Crippen begin checking their systems. One of their first major tasks is to open the large payload bay doors, a crucial step to deploy the ship's cooling radiators. As the doors open, the crew looks out the rear windows and spots a problem. Several of the heat-resistant thermal protection tiles on the rear orbital maneuvering system pods are damaged, and some are completely missing. This is a major concern. If tiles are missing from the top of the ship, they could be missing from the underside as well. But the astronauts have no robotic arm or spacewalk equipment to directly inspect the belly of the orbiter, which takes the brunt of the heat during re-entry. Down in Houston, Mission Control has to evaluate the risk remotely. Engineers scrutinize televised video feeds sent down from the shuttle, studying the visible damage on the pods in real time. After analyzing the images, the thermal teams conclude that the specific locations of the missing tiles on the upper pods will not experience peak temperatures during the plunge back to Earth. They clear the crew to continue the mission. It was impossible to guarantee a flawless flight on an untested spacecraft, but the response from Houston demonstrated that the ground teams could rapidly analyze an unexpected physical failure and make accurate survival calculations on the fly. At the end of the 2-day mission, Columbia fires its engines to break out of orbit. Once that burn is complete, the laws of physics take over. The vehicle must land. Unlike a commercial jet, the orbiter does not use engines during its descent. It drops through the atmosphere as a 100-ton unpowered glider. This diagram illustrates the descent profile. Because there is no thrust, there is a continuous, steep drop toward the runway. The crew has zero margin for error. They cannot throttle up to correct a low approach, and they cannot circle around to try again. As Columbia hits the denser layers of the atmosphere, extreme friction wraps the vehicle in a sheath of superheated plasma. The airframe relies entirely on the silica tiles to prevent the aluminum structure from melting. Every engineering compromise, every weight calculation, and every thermal tile bonded in the factory converges in this single moment. The entire design of the shuttle system is tested by this one unpowered plunge to the surface. Dropping out of the sky, Columbia flares its nose, lowers its gear, and touches down smoothly on the dry lake bed of runway 23. The landing takes place at Edwards Air Force Base in California, closing out a 36-orbit journey. By surviving the launch and the landing, STS-1 provided engineers with the actual aerodynamic and structural data they had been missing. They finally had hard evidence to validate the concept of a reusable orbital spacecraft. The unexpected lofts, the timing glitches, and the damaged heat shields provided lessons that static simulations never could. Navigating the unpredictable realities of this maiden voyage laid the factual foundation for the next 30 years of the Space Shuttle program. Thanks for watching. If you want to see more deep dives into aerospace history, like, comment, and subscribe, and be sure to share this video with a friend.